Hi everyone, Mr. Roloff here, and today we're going to talk a little bit about half-life. Really a half-life is how much time it takes an atom that's radioactive to decay. So if we look at this intro picture here, we'll start with some atom, some sort of isotope of an atom, and after a given amount of time, and this changes for every isotope that decays. It has its own unique half-life. The amount of time it takes for 50% of that to decay, to change into something else. So you'll see that after the first half-life, we only have half. After a second half-life, we have half of that 50, so now we only have 25% or a quarter. And then after a third half-life, right, now we took that 25%, we cut that in half, so we're at, what is that, an eighth? So after that given amount of time, we're just basically chopping the element in half. So let's take a look at a sample problem here. I'm going to do two problems with you, so please follow along. We're going to start with number one, and it says a fossil of an unknown age is found. Scientists determined that the carbon-14 to carbon-12 ratio in the fossil is 1/32. That's going to be important. All right, so I'm just going to highlight that real quick, of the ratio found in living substances today. So we're going to calculate the age of the fossil. All right, that's also going to be important. We're finding age of the fossil. Here's probably the most important piece here, the half-life. You're not expected to memorize these half-lives. They're always going to be given to you. So the half-life of carbon-14 is 5,715 years. So there's really two ways to go about answering these types of problems, half-life problems. The first one you could do that I really like because it's pretty much foolproof is you can start by just drawing a picture. All right, so just like you saw on the previous slide, I'm just going to draw my element. So at the start, right, that carbon-14 is full, and then we're going to undergo a half-life. So that half-life is 5,715 years. And then after that amount of time, we're going to have half of that, right? So we have half of that amount. So we need to do that. So here we're starting with 1. Here we've got a half. And we're going to continue to do that. So another 5,715 years. And now we have what? A quarter. All right. Another one. Now we're up to an eighth. I'm not much of an artist, but you get the idea. Notice I kind of quit doing the drawing. Now we're at 1/16. And then the last thing, or I quit putting 5,715 on every arrow. Just know that they're there. And then the last sliver here puts us at 1/32. So what I can do now is I literally, by drawing this, all I have to do is I could just add these up, right? 5,715 plus 5,000. Add everywhere there's an arrow, right? Remember, every arrow is another 5,000 years or so. Another way I could do that very easily is I could take 5,715, multiply it by how many arrows there are, which would be 5, and I would end up with my answer, which is 28,575. Make sure you have a unit, years. So that's one way of going about this problem. I'm going to show you a little bit faster way using a reference sheet that we let you use. So here's an example of that reference sheet. So you want to bring this with you. You can use this on the come test time. And if we dive into, this is kind of quite a bit of information here that's helpful to you. So you'll notice that around here you can actually see that, full original radioactive material. After one half-life, we have half. Here's where we're going to use the most data right there is if I look, and remember that problem asked me to calculate how old that sample is, what was the age of the fossil. So what I can do is, if you remember, it said that there's 1/32 left over, right? So I'd find 1/32. So I'm focusing on really this line right here. Notice it tells me, if I use this sheet correctly, that it's gone through 5 half-lives. So I can essentially make my life a little bit easier by knowing that it's gone through 5 half-lives. If I know how long each half-life is, which it tells me, the calculation's pretty easy. So this might be something that you want to add to your study sheet when you're getting ready for the test. These are just two I guess, helpful tips or steps on how to actually do a half-life problem. So if we're looking for the age of the sample, which is what we're doing in this one, we're going to follow those steps. And what we'll do in the next problem is we'll look at sample size. If we're trying to find sample size, rather. So let me just gloss over these steps really quick. Step 1, determine how much sample is left. Well, we did that. We said that that is, what, 1/32. We get that from the problem. Okay. From there, I'm going to figure out how many half-lives we've gone through. And we did that as well, didn't we? It was 5 half-lives. And then from there, all I have to do is take the number of half-lives, which is 5, times the amount of time for one half-life, which was, what, 5,715. Multiply that out, and we get our answer. So it's really more of a short, more efficient way of really getting the same thing, right? I'm taking the number of half-lives after I look on that chart, and what I'm basically doing is then I'm 5 times that 5,715. I still get 28,575 years. So it's a little bit of a shortcut to get away from maybe drawing all those pictures out, but either way is going to get you to the correct answer. So let's take a look now at a different problem where we're trying to figure out how much of the sample is left over. So for that, we're going to scroll down. We're going to tackle number 5. So number 5 tells us, hey, there it is again, our half-life. I'm just going to underline that. The half-life of polonium is 138.4 days. And it says, how many milligrams of polonium-210 remain after 415.2 days if you start with 2 milligrams? So I'm starting with 2 milligrams. So what I'm going to do here, again, I'm going back to that picture method. So this is always an option. We're starting with 2.0 milligrams, and that's going to decay over a period of, what, 138.4 days. Okay? So after that 138.4 days, I'm going to have half of that. So half of 2 is 1, right? 2 divided by 2 is 1 milligrams. And I'm going to continue to decay that. Now, one area that students mess up is they'll put the half-life not over the arrow, but actually over how much is left over. And if you look back, you'll see that if you do that, you're going to have one extra half-life. You're going to actually go too far or end up short. So make sure that those half-life times are over the arrow. And after that, now I'm going to have, what, 0.5. So at this point, how far do I go? What do I just keep doing this until I don't know when? Well, it tells us in the problem here how much will remain after 415.2 days. So what am I at now? 138.4 plus 138.4. I'm at like 276.8, I believe, if I were to add those up. So I got to keep going until I hit that 415.2. So I'm going to do another one, 138.4. Now I'm at, what's half of a half? Oh boy. 0.25, 0.25 milligrams. And if I check 138.4 times 3 gives us that 415.2 days. So at this point, I'm at 415.2 days. If I add up all of these half-lives, all of these days, it adds up to 415. So I know that my answer is this right here, 0.25 days, or excuse me, 0.25 milligrams. So let's try to find a shortcut, just like we did in the previous problem, to help us maybe do that a little bit faster. So let's go back to these helper steps here. Since this is asking how many milligrams are left, or what's the original mass left over, when it's looking at how much is left over, how much versus this is really time. I'm going to follow these steps now. So I'm going to, step 1, I'm going to determine how many half-lives have gone through the age of the sample, or the time, and divide that by the time of 1 half-life. So let's just map that out. The age of that sample is what? 415, excuse me. Okay. 415.2 days was how old that was. And the half-life I underlined was 138.4 days. From there, I'm going to divide those, and what I find is that it has gone through 3 half-lives. So from there, what I can do is I can then, step 2, determine how much is left over, what fraction is left over using that half-life chart. So let's take a look at that. If I went through 3 half-lives, I have 1/8 remaining, or 12.5%. So I'm going to focus on this 1/8 remaining. So I'm just going to update my chart here. I have 1/8. That was the fraction of the sample left over. So now I'm going to calculate the sample size. My original sample size for this problem, if you remember, was 2.0 milligrams. If I multiply that by 1/8, I'm going to get an answer of 0.25 milligrams. Oh my gosh. It is literally the same. So here's kind of what you can have for your work, because obviously we should show a little bit of work here. But if this makes sense, if these steps make sense, you can show me that it's gone through 3 half-lives, and that's going to mean that 1/8 is remaining times 2.0 still gives me that 0.25 milligrams. So again, a little bit faster, a little bit easier. You're always welcome to draw pictures, even on the test. If you have pictures all over the place, that's great. We just care that you know either how old that sample is or how much we have left. Hopefully this video helps. If you have any questions, please talk to your instructor. Thanks. Encore, encore, we want more. Oh, I forgot number 8. Let's check it out, though. So if what we're doing is we're basically writing this decay series for uranium-235. So what you'll want to do is, I'll just do the alpha decay, starting with uranium-235. Look up on your periodic table. You want to have your periodic table. Uranium is 92. And what that's going to do is it tells you it's going to alpha decay. So what we'll do is we will be alpha decaying that. So a 4,2 helium is going to come out. If you remember that an alpha particle is that 4,2 helium, we want to know what's left over. So remember, the left side of our arrow needs to equal the right side. So if we have 235, 4 plus, you got it, 231 is going to equal 235, and then 90 plus 2 gives us that 92. What's element 90? It looks like it is thorium, TH. So then what you'll do is, for the next step, is you'll then take what's left over, that 231 thorium, and we're going to beta decay that. So remember what a beta particle is. It's really an electron coming out of there. So again, thinking of this arrow as almost like an equal sign. 0 plus, that's easy math, 231. What does change is our atomic number. And this one you got to be careful about. -1 plus what gives me 90. Right now, I can double check my work here. Oh, that wasn't right. My math is a little bit off there. Not 92, but 91. So 91 plus a -1 is the same thing as subtracting, right? So 91 plus a -1 gives me 90. So this atomic number actually went up, and 91 we find is Pa, all right, on the periodic table. So you'll do that until we get to lead 207, which is what your final answer will be. So hopefully that helps. Have a good one.